if we have a Laplace transform of phi, then using that one, basically is phi divided by s. You simply scaled up. And if we have a time function t, so that means, say, if we do the integral 0 to infinity t e minus t dt, okay, that is put into the fundamental definitions, then the result will be equal to 1 over s squared. And like we did this here, okay. So this will be the handy the tables, and EAT we think that is 1 over s, and this one, basically the things is if you multiply the t to the n power, then basically equivalent in this way is the n, the series multiplication, and then s minus a n plus 1. That's kind of the rule there. And so for sine and cosine, this also commonly seen, and that is this and this. And for the two functions combined with exponential function, then later we will have a little bit more discussions and how to utilize the features. Okay. The delta, if you like, you can put down to your notes. The delta is called the unit impulse function. Okay, so if this is the t, the time domain, if this is t equal to 0, so basically here at the time 0, if we say, I knock this, sorry for the next room, and here I apply to the whiteboard is an impulse, okay. If I can control my magnitude and I can make it as the unit impulse, so that means the magnitude equal to 1, and this is called the delta t, okay. So another way, if I start to count, okay, I start my process 0, 1, 2, 3, 4. At the time at t equal to s seconds, I fired another impulse function, then this is called the delta t minus a. That means this is a unit impulse function fired at time equal to a. We good? Okay, so that is these things. So for the impulse function, depends on what moment you fired, the corresponding is this one. The second category is about the combinations of the function. So here you can see this is a linear combinations in the time domain. The same thing, linear combination in the s domain in his the Laplace transform counterpart there. So this is the derivative. So derivative over time. So that means is the dot. Okay, the first derivative, and the f double dot. Basically, most of the time is x of t, like this one. Okay, so I simply use the different notations. Hopefully, you understand. Basically, this is the first derivative and nth orders of the derivative, etc. Okay. So for example here, let me make one example here. So for example, if we have functions and arbitrary certain functions, it's the Laplace transform. Let me define using the symbol capital of x. Okay. So then we do the say if we want to find the Laplace transform of the first derivative, then using that equations. Using this equation, right now n equal to 1. N equal to 1, so that means you copy carefully, look at your handout, that is s, multiply with capital of S. Okay, and right now n equal to 1, right now I'm writing is this term. We good? For the second term, when n equal to 1, that becomes 1, f0, that means initial conditions of x. So that this means initial conditions of x of t. Okay? And now we continue. And most of the time we're dealing with is the second order differential equations, which means the vibration systems. So that is the one. So here again we apply this function, this equation here. Now we set up n equal to 2. Okay. So that is s squared multiplied with x of s. And then the second term would be s and then multiply with x dot 0. You see that one, oh sorry, is this one, okay. And then we'll continue to the very end. So when n equal to 1, so that is the last term is the first derivative of this one. Very good? Yes or no? Okay. So everyone have any questions about this term? Good. So now let me make one example here. So now say if consider we have divergent systems, and for whatever reason we are able to formulate its equations. So for example, 5x double dot plus 3x dot plus 2x equal to 1. Okay, so that is certain systems. For example, here the system can be represented by this. And this is 5, and this is 3, and this is 2. So spring index has 2, and the damper coefficient is 3, and the mass is 5. For this single degree vibration systems, and this is the degree of freedom x of t, then the dynamics of x of t can be described by this if we are given the certain kind of the input here assigned to 1. Okay. So for example here, say we have an initial condition, say this is 0, and x dot and equal to 1. Okay. And let me put that in general. So let me say, how about say this is A, this is B. So we can apply the Laplace transform tables to see. So now I want to take the Laplace transform of the whole thing. We see what happens. So we take the Laplace transform of everything. Okay, so now the first one is the Laplace transform of the x double dot. Again here, let me quickly write it down here. That one we have the things here already. So, and then x Laplace transform of the second terms here, and we have these things here already. Okay, and then the last one, x, and this one basically by definition we're using these symbols. Okay. So we have everything here, then we simply plug in those Laplace transform. So basically this one will become like this. 5 times the Laplace transform of x dot plus 3 Laplace transform of x dot plus 2 Laplace transform of x and equal to Laplace transform of 1. Okay, so we do these things individually. And from here to here, I applied it in the first property, the property here. The linear combination in the time domain corresponding after the Laplace transform is still linear combination in the S domain. Okay. So right now I apply that one, and then we simply plug in individual. So this one is available here, okay, and this one is available here, and this one by definition is this one. So we simply plug in, see what happens. So that means here, let me plug in 5 and s squared and capital X, and let me kind of ignore the right of this one, and minus s x 0 and minus x dot. Okay, and plus 3 s capital X and minus x and plus 2 capital X. Okay, the whole thing is equal to Laplace transform of constant, and one that is 1 over s. So this is 1 over s. Okay? Okay, so let me erase this part here. So right now let me arrange. So here you can see we have these Laplace terms here. Let me turn off this term. Capital X, and that's a function of s, and we can put there, that is 5 s squared plus 3 s plus 2. Okay, so right now I make these terms 1, 2, 3, and leaving the remaining. And this one, let me plug in x0 is A, and x dot 0 is B, and this is A. So let me replace the given information. So that will be equal to minus 5a times s. Okay, so right now I have this one done, and then minus 5b minus plus 2a. Equal to 1 over s. Okay? So in this way, we can have the x of s, and that will be equal to 5s squared plus 3s plus 2, and then that is 1 over s plus 5a s plus 5b plus 3a. You good? Okay. So the next step is we simply take the inverse Laplace transform of x, capital X, and then we will, this one by definition is x of t. So how to take the inverse Laplace transform of the everything's here into here, that will be the another thing that I'm going to help you to review how to do it. Okay, but at least right now, everyone should be good with this one. You good? Okay. So that is the one, and let me still continue to here. So this one we can convert to refer to this one. So the multiplication of the t to the n power corresponding is take the derivative in S domain, and if we take the exponent, we have those things. And now for this one, what is h? H is the particular function we call the Heaviside functions. Again, the h is similar to the things, that meaning you can see for this function is equal to 1 when for every time the t is greater than a. So basically this is simply a step function which is fired up at t equal to a. What is a step function? Unit step functions. A unit step function usually we is t, and so usually we use the ut. So that is magnitude equal to 1. So that means that function is always constant equal to 1. Okay. And so for example here, if we have the unit step functions, and that is fired up at t equal to a. So that means at this moment, this one is simply, you can use is ut minus a, or you can simply use ht minus a. Either symbols will be good. Okay, so basically the Heaviside function is simply a unit step functions, and that's being started not from 0, right? However, it's starting from a. Okay, so for these functions, so you may ask me what this means. That means is this: if you would have okay, so if we have any functions simply like this, okay, and the function behave like this, and arbitrary function simply throw it up. And what means the ht minus a multiplied with this one? That simply means you pick up the behave or response of the functions from this moment and onward. Okay, good? So that means these functions, because it won't be activated before t equal to a. So before this moment comes, everything will be lying down inactivated. So that means here in this way, before the a, then everything will be disabled, I would say. Okay? Okay. And then what is t minus a? So if we have the functions, and this is t, and this is a here. So here the t, ft minus a simply is to do the shifting in the time domain by that much. So basically here, this curve simply is the shift to here. So let me copy. If I have the in PowerPoint, I can copy this curve, the black curve, and this is the black curve. I can copy that one and then move to here. Okay? So that is called the time, the shifting in the time domain. So that is the meaning of this one. You good? Okay, so that means when we combine the both together, basically it simply is this. We have the function won't start it until t equal to a. So can you see the difference? And everything beforehand is 0. You good? Okay. This is a periodic functions in time, and then there's a formula here. Okay, so this is a convolutional integral, and that corresponding to we call the impulse response, and we have one small section, so I'm going to explain this one, and now you just take it, okay? And yes?
When this type of technique used to avoid the initial noise or something like that?
Initial noise?
Yeah.
We just simply don't take count. We don't consider those things. Okay. And we have two very good theorems in the plot transform. And one's called the final value theorem, the other initial value theorem. This one, and make a mark here on your notes, this one is going to use a lot in controls. This one, no. Okay. So if you like, you can put the start mark here. And this means, what this means? This means the value of the function when t approaching to infinity, basically one word that called the steady state response. The steady state value of this function. Okay? So using the, we can say this is a steady state. The whole term representing the steady state value of ft. Okay, and if we want to calculate the steady state value of the functions, then simply we calculate like this. Okay, this function, this theorem will be used later on in the analysis of the steady state error. Okay, and I will remind you that one. Okay, so those are the quick overview of